Yay. Sorry, this is my first time giving a keynote, and I might be a bit excited, but I got this. So today I will talk about multimodal AI, and if you don't know me, I'm Merve, and I go by as open sourcer in machine learning. I've been doing open source for full time since 3 years, and I really enjoy it. And I currently work on multimodal AI, which I will come to later on. And I work on zero-shot computer vision most of the time. But what is multimodal? If you are coming from traditional data science backgrounds, etc., you often do not need these type of things. So I wanted to define a bit. So if you have 2 or more modalities in machine learning, it's called multimodal. Good examples are GPT-4v, for instance, inputs image and text and outputs text. It's a multimodal model. Stable diffusion, I would say, is a multimodal model because you input image, text, and output image. You can have text-to-audio models like speech synthesis or vice versa. So if there is 2 or more modalities in a model, it's called a multimodal model. Today I will specifically talk about multimodal computer vision because it covers the whole paradigm of multimodality very well, and also it's particularly what I'm working on. There are multiple types of multimodal models in computer vision. The most known are the vision language models, which GPT-4v is a part of, or any other proprietary model that you're using that is very popular. Another one is multimodal retrieval models, which is COLPALI. It's not as popular right now, but I think we will hear more of it later on. There are open vocabulary, image classification, object detection, segmentation models, which I will come, but essentially, you input any text that you want. It is not restricted to a certain set of classes in the training data, and you can segment anything, you can detect anything, you can classify anything. And open source examples of these models are recently for vision language models. The most popular one is Lava, Q12VL, InternVL, and Polygemma. For multimodal retrieval, as I said, this is a new paradigm. There is COLPALI, but also there are some models like CLIP or SIGLIP that you can also use for multimodal search. And for these ones, so there is, as of now, the most popular open vocabulary object detection models. There's 2 of them. One of them is OWL model by Google Brain, and the grounding Dino by Alibaba. And then I have combined OWL and segment anything, which I will come later, to get the OWL-SEM, which is an open vocabulary image segmentation model. So for the first ones, also Polygemma was released by Google, and Q1 is a team at Alibaba releasing these. But why does it matter? So, as usual, why should I be using open source models instead? So firstly, you can have the utmost control over your models. You can do local machine learning, as in you can have it on your local devices. You can have it in browser, for instance, to actually guarantee the privacy for your end users. You do not, so basically when you rely on a cloud machine learning platform or when you rely on a proprietary model endpoint, the model in the backend can change, and you do not necessarily know how it changes. So when you have the open source model, you are at least prepared for those cases. And that's why open source really matters. And open source is actually catching up. So this graph is from Maxime Labonne. This is for large language models. But essentially, vision language models are based on large language models. So, and the vision language models are sort of a recent paradigm, so it will eventually catch up with the closed source models. But as you can see here, with the recent Llama 3.1, we've already caught up with the closed source models. And this is a score called Arena ELO, which is like based on preferences of users. Essentially, you are seeing two outputs of models blindly without knowing which model is which, and then you pick the one that is more suitable for you. I think it's the most reliable benchmark as of now. And Llama has already caught up. So, common use cases for multimodal models. First one, and the most obvious one, is the document AI. Reason why is because most of the documents are very complex. If you have a plain text document, you are all Gucci. Like, you can just go for OCR or whatever. But if you have charts, tables, layouts, and more things, images in your documents, it means that you rely on something that is multimodal. Another thing is image understanding. You might need it. There are so many specific use cases. For instance, captioning is one of them, or visual question answering is one of them. One of my favorite ones is image search in gallery. Like when you go to your phone and you type in your gallery, you know, a tabby cat, it always brings the tabby cats. It is essentially the best example for the open vocabulary image detection, image classification, and because of this, this technology is enabled on our phones. And lastly, you can use mostly zero-shot models for data labeling, which is a bit of an advanced use case. So this is a keynote speech, and we have everyone from all the levels in the room, so I will not go into very deep technicalities, but after the talk or during the question and answer, you can ask me technical questions. I do not mind. So starting with CLIP, it's a model released previously by OpenAI, which changed the paradigm, in my opinion. This model is essentially trying to optimize the most similar captions and match the most similar captions to their images. And it is like a neural network which has an image encoder and text encoder, and then they are joined trainedly backpropagating the loss to the both of them, so they are sort of aligned together. And this way, you can do image search. For instance, you have a gallery of images. You can just index them with the clip, meaning you can get the embeddings of these images by passing them through clip, and then search among those texts and images from text to image or from image to text. It goes both ways. With clip-like models, you can do anything. Essentially, the image search on your gallery is likely a clip-like model. Another thing is you can use it for zero-shot image classification, which is what it relies on, honestly. It's the same use case. I will come to how it's used later on again. But for now, the most advanced clip-like model as of now is SIGLIP by Google. It's essentially clip with sigmoid, so hence the name SIGLIP. And as you can see here, I have an image, and I have some candidate labels, like 3 labels to classify this image with. And you can see B on the flower comes the most probable. By the way, these are not the probabilities. They do not add up to 1 because it's sigmoid output. So it's not normalized, thus they do not add up to 1, but still it returns the sort of the, how do you say, the similarity score. Another model that I have previously mentioned is OWL model by Google, which is a bit like CLIP again, but with the sort of trained for object detection, like bounding boxes are matched with the most similar captions in a way in the image. And this is the V2 version of OWL is the state-of-the-art zero-shot object detection. You can use it for stuff like, for instance, if you have an object detection problem and you do not have the labeled data, you can start labeling the data with this one. So for instance, this is how it's used for tracking. And open vocabulary segmentation, but we will first go to the mask generation before that. So it is essentially to input an image and some text and get the segmentation mask as the output of what you would like to search for. And it's open vocabulary again, so you can input anything. But firstly, to go through the mask generation, it's a task that was introduced with the segment anything model by Meta. I think it was last year, and this year they have released another model called SAM2. This is essentially inputting a bounding box surrounding the object of interest or leaving a point on the object of interest, and then you get the mask of that object that you wanted to segment. And this is the most state-of-the-art model now. Essentially, the change between SAM to SAM2 is they have added a memory module which stores something called masklets, which is like segmentation mask over time, so you can track any object. And it works pretty well. This got me really excited this year. As you can see here, it's pretty good. So I combined two models to make the segment anything model. Because segment anything model doesn't accept the text input, I have combined two models to make it text promptable. So I enter the text caption to the image and to the model and the image itself, get the bounding box, and then prompt that bounding box to segment anything model to get the captions. So this is the most advanced open vocabulary segmentation model, essentially. So most of my talk is actually focused on vision language models. I just wanted to give a mention to great models out there. And also, CLIP is needed to learn about these models as well. So wanted to give a quick introduction. So vision language models can essentially do anything that large language models do, but also input image. You can do object localization, for instance. It can understand spatial. It has spatial understanding. It understands the location properties of semantic classes. It can do zero-shot segmentation. As you can see here, I input image and say segment striped cat, and I can get this output. It can do visual question answering and one-shot learning, which is like in-context learning in a way, or like one-shot prompting with instructions, and then I get these outputs. Sorry. And how did they start to begin with? So there is, for the open source part at least, there is a model called Lava which changed the paradigm pretty much. They have taken a clip-like model. So you have this clip-like model which can understand both image and text. Okay. They have taken the image part of clip, and they have taken a language model. You can think of anything, any favorite open source large language model of your choice. But if you don't know any of them, just think of GPT-4 or GPT-4 or whatever. And put a projection layer between them, which is often a multi-layer perceptron, nothing fancy. And they have frozen this vision encoder and large language model, and then only trained the projection layer to understand how they relate, sort of, to align them. And then I think I'm going to show, yes. So initially, they freeze the image encoder and text decoder, and then just train the multimodal projector. And on the second stage, they've either freeze or unfreeze the image encoder, and then train this whole thing on, for instance, instructions or chats. So this is how most of the vision language models work these days, for at least the open source ones. And there is 3 types of them. First one is the base model, which is like models that can be used for fine-tuning. Second one is chat model, base models that are fine-tuned on chat data. And third one is the instruction ones, which are base models fine-tuned on instruction. So PyGemma is a model released by Google this year, and this is not a very big model. It's 3 billion parameters, and it is very good for fine-tuning. That's why I wanted to show you. They have released a bunch of checkpoints. If you're interested, you can just go and type PyGemma. It is also the first model that can do open vocabulary segmentation, which was pretty amazing to me back in the day. I can explain the technicalities if you ask me later on, but not now because it's a bit complex. I actually discourage using these models for object detection and segmentation, though, because technically, both the OWL model and PyGemma or whatever have the same image encoder in the end, and one is more task-specific. I always encourage using the models where they are needed, as in you do not use LLMs for text classification, but actually use a text classification model like BERT or what you want for text classification. So this is the same case. I discourage using these models for these cases and actually using a segmentation or detection model. Q12VL is my favorite model these days. It was released by Alibaba. It has amazing properties. It just understands very well. As you can see, this OCR, I couldn't even read this, and it was able to explain what is this about to me. And it understands multiple languages, even Icelandic, which I have no idea about, and it was able to understand the Chinese some of the low resource languages I tested was working very well, because most of the models in open source unfortunately come out for mostly English and most high resource languages. I think it's a very important work that they work for low resource languages too. And if you are doing this, if you have, so basically most of the time people do retrieval augmented generation by OCRing the documents, passing them through an OCR model, getting the text, getting captions for the images inside documents, and then compiling this messy text and passing it to LLMs. Please do not do this. It's really not. It's very brittle. It is hefty. Try this instead. So take images, okay, and pass them through call_poly with the text query that you want. It will bring the most relevant text and their scores, and then you can pass the most relevant document to the multimodal model, because it is already an image. You do not have to parse it with heavyweight image captioners, table readers, markdown generators, or whatever. No, we don't do that. And believe me, as of now, for you, most of the time it works well. Some people reported some issues to me for their own use case, but believe me, this will get better, because unfortunately for multimodal, it's a new paradigm, so we are getting even better by now. And how do you get started with this? I work at Hugging Face, thus I'm a bit opinionated, but I will tell you some Hugging Face, non-Hugging Face alternatives of what I'm mentioning later on. So, first, how do you find the model? So, essentially, you find the model. If you need to customize or customize it, as in, if the general model is enough for you, you can quantize it to cut your costs or prune it or whatever you want. If it's not enough for you, you can fine-tune it on your own data, and then you can deploy. So first, how do you find the models? Hugging Face, if you don't know, is like very much a place to find models these days. And you can go and filter for image text-to-text, which is a cryptic name for vision language models. And then you can see there is like 593 vision language models on Hub right now. There are a bunch of other things, like you can also find text generation models or whatever you want. But if you would like to actually evaluate them, there are multiple things to evaluate these models on. So there is something called OpenVLM leaderboard, where where models are evaluated on certain benchmarks. Most popular one is MMMU. There's a bunch of them, like MatVista or Hallucination Bench or whatever. You can go and rank the models according to your benchmark that you want to use. You can also see if, as you can see here, the benchmarks, model type. So some models might be open weight, but not open source because of their licenses, so pay attention to them. Look for MIT or Apache 2.0 licenses. They are your friend. If you have like a specific hardware restriction, you can also filter the models for model size. And for NVIDIA GPUs, for instance, these are what you can use. And if you have all the hardware in the world, just go for bigger models. As of now, they just work very well. If you have found your model and you want to deploy it directly, you can use text generation inference. It's a toolbox developed by Hugging Face. It is completely open source. It provides optimized inference for vision language models, also large language models as well, but this talk is themed vision language models, so just so you know. It provides quantization support as well. You can do token streaming. And you can do also optimized inference techniques like tensor parallelization if you have multiple GPUs, for instance. And the API is super simple. You just, especially with Docker, you can just serve with one line of code and then just query if from Python, from JavaScript, from curl, however you want. So if you want to customize your model, there are a bunch of libraries that we have. Of course, most famous one is Transformers. I think most people know it. It is a library where most of the state-of-the-art, cutting-edge architectures are abstracted and provided with a very simple API, which I will quickly show you. So it provides for vision language models inference and fine-tuning support and quantization support as well for all models. Only for zero-shot object detection, mask generation, and some of the vision language models, it provides something we call pipeline, which is like 3 lines of code inference abstraction that is super simple. And this is, for instance, I made a mistake over there, but this is how you initialize a model. So each model has some class according to the model architecture. For Polygamma, it's called Polygamma for conditional generation. You initialize it with the from pre-trained method of that class, passing in the polygemma checkpoint on Hugging Face hub that you have found, and you can initialize the processor of that model as well, and then you can just start inferring the model. So for instance, you input an image, and you input what is on the table as a prompt. You process them first. They have to be processed, as in, if you know the terms tokenized or images have to be processed, they have to be processed. And then you pass it to model.generate. If you know PyTorch, this is very easy for you. And then you have to get the output and then call decode, because they return as tokens. You have to decode them to human readable version, as in words. And you can get the output like this. Like inference is this simple. So there is another thing. If you would like to have more memory savings, you can use 4-bit and 8-bit quantization. It's supported by a library called Bits and Bytes, and this library is just supported at Transformers. All you have to do by means of API is, according to the previous slide that you have seen, just add this import bits and bytes config from Transformers, initialized quantization config, and only pass that to the model initialization, and rest is the same. There is no API change. It's super convenient. And for pipelines, I wanted to show you, pipeline is actually one line of code initialization for this whole processor, post-processor, whatever decode, all of them in a box. It's super nice abstraction. You initialize, so you import pipeline from Transformers, and then you initialize the pipeline with the model of your choice and the task. For this case, OWL is a zero-shot object detection model. And then you pass to the pipeline that you initialized the image and the candidate labels, or like whatever input that you have, and you get the outputs. That's it. Last couple of bits, there is another thing called parameter-efficient fine-tuning. If you have ever heard of LoRa, that is a parameter-efficient fine-tuning technique. So if you have if you would like to save on money and time you are spending on fine-tuning language models, vision language models, any model in machine learning, you can use parameter-efficient fine-tuning. There are multiple methods for this, but I think most famous one as of now is LoRa and QLoRa. QLoRa is essentially LoRa, but the weights are quantized to 4 or 8 bits. And sorry, I was a bit sick coming here. The LoRa is handled like this. You initialize a LoRa config. These often are not as custom as you think they are. You can just go with what most people have tried. And initialize the bits and bytes config if you are doing QLoRa. And just initialize the model like you would with Transformers, only passing in quantization config. So basically, LoRa is adding an adapter on top of a base model. An adapter keeps the changes in the weights. That's why it's very efficient. And you just put the adapter on top of it, and you prepare the model, and you essentially have less parameters to train. That's why it is very efficient. Another thing is transformer reinforcement learning library. So the whole reinforcement learning from human feedback, the whole paradigm change also reflects on the open source. We have a couple of methods. One of them is direct preference optimization, DPO. Other one is just supervised fine-tuning. These are adapted for vision language models as well. And there are two nice abstractions. One of them is SFT trainer, other one is DPO trainer. And these are essentially easy to use classes to apply these techniques on vision language models. And they also support LoRa and QLoRa as well. So again, for TRL, you start with initializing a TRL parser and getting some training arguments. The rest is the same. As you can see, you are initializing a class. Here it's Lava for conditional generation. It's a model class. You initialize your classes, and you just initialize SFT trainer or DPO trainer with your model that you have initialized here, and the training arguments that you have initialized above, and call trainer.train and trainer.push to hub if you would like to push it to Hugging Face Hub. But this is a very simplistic API to apply cutting-edge alignment techniques that are used to get state-of-the-art results with the LLMs and VLMs. And really, the last thing, if you want to apply quantization, there are a few libraries. There is Quanto, and which is very similar to Bits and Bytes, in my opinion. But I think it supports more backends. And there is Optimum, which is more widespread, as in it has graph optimizations, more types of quantization than 4 and 8-bit, and so on. And this is my project, Small Vision. Please check it out. It has all the notebooks to fine-tune VLMs. You can quantize zero-shot models and so on, fit them into whatever hardware that you want. This is my love child. It was actually in GitHub trending last week. So I really would love you to check out, because I really build it for people. It's like a hobby project for me. Thank you. Do I have time for questions?
All right. Thank you so much. Are there any questions from the room? I will come to you with the mic if you have a question for Merve.
Please do not hesitate. What I have told is like state-of-the-art cutting-edge stuff that most people do not know about. But if you have questions, please do not hesitate. There is no such thing as stupid questions.
I see a hand. I will come to you.
Hi, am I audible? Yeah. Yeah, so this question is just regarding the multilingual model, Queen V2.
Can you raise a hand? I cannot see. Oh, okay. Okay, hello.
Yeah, so regarding the model Queen 2 VL, have you tried like the language, Dutch language in it? Like, does it work well with
Dutch language?
Yeah.
I haven't, but I am sure there is something inside about it. Like most random languages I have tried and it was working. So
okay.
I really
Sounds
believe,
good.
Yeah.
We have another question here.
Thank you so much for the talk. I had a question about biases in general, and you also see biases in language models, but do you also see biases in visual language models? And if so, is there steps to solve these biases, right? Because language models have context. Images don't have a lot of context embedded in it. Yeah.
The question is, essentially all vision language models are large language models with an image encoder on top of it, and that image encoder is mostly not the part that introduces the biases. So I would say all vision language models are having biases or hallucinating as much as large language models. So for instance, if you had a workflow where you are already using a large language model, and if you would like to swap it with the vision language model, it will likely have as much hallucination or bias as much as the large language model most of the time. I don't know the current suite of the large language models. I don't know how much bias they have, though, because we currently have a lot of data sets to align them, and those data sets are mostly curated and filtered by humans. Some of them are generated, but also, again, filtered by humans. So, like, it really depends on what model it is. Any other questions? Yeah.
So you said that if we have a document which mainly consists out of text, be it in a already OCR form or in the form of a picture, you would just go for OCR and then apply some large language model. But if it's a document where you really need to understand also take into account the pictures to understand the document as a whole, then you would go for the models that you just presented. My question is about documents which are, let's say, in between the two extremes. Because if, for example, you have a web page where the text is not, if you look at it as a human, you can basically guess in what order you have to read it. But if you look at the CSS code in the background, it's really scattered, and the machine is not really able to, determine what is the right order of text. What would you do in this case? Is it more? Would you more apply, take a snapshot and then apply the techniques that you just presented, or rather try to reconstruct the text in the background?
The thing is, the missing context from this question is the fact that I don't know if you are inputting screenshots to this system and getting CSS code, or if you are inputting screenshot to this system and you have some information that you would like to extract, like a meaningful information, like you are asking a question to a web page and getting an answer out of it. Like, what is the input and output of this system?
It's about the content of the text that is displayed to the human. The CSS is not of interest. It's just actually an obstacle.
Then you should definitely input screenshots and use the pipeline I have shown you. And let me know also how it works. There are some vision language models that are fine-tuned on web page understanding that you can use for this, and you can just get the answer.
Thank you.
Do we have time for more questions?
We have time for one more question. So if there is one more question in the room.
Okay. There is one.
We have one over here.
Hi, Merve. Compliments for the presentation. You spoke about open vocabulary.
Where is the person? I can't.
Hi.
Hello.
You spoke about open vocabulary in order to detect objects. What stops us from inputting images instead of text in order to detect the objects? Or is this something that hasn't happened yet?
Can you rephrase the question? I don't understand.
So, for example, in the old Sam example, you said find two white-gray cats. If I would input an exact image of my cat, can old Sam replicate the experiment?
Replicate as in detect bounding boxes, you mean?
Yeah, of this specific cat.
Yes. It is, again, open vocabulary. It can input any text. You can input any text. It doesn't have to be a specific class.
But if it's image and not text?
No, you are inputting both image and text to the model and then getting the bounding boxes out of the image.
Yeah, so maybe the question is, what if I input two images? An image of a cat and an image in the wilderness, and I tell it, find me this specific cat.
You mean image-guided detection?
Yes.
It can do that. It can do image-guided detection as well.
With all?
Yes. There is some example in our Transformers documentation. You can just refer to that.
Brilliant, thank you.
I have brought some Hugging Face stickers. Unfortunately, they are not a lot, but just join me if you would like one. Thank you so much.